Hi Honors Bio students, this is a short video tutorial on how to make a simple graph with error bars in Excel. Most of you have collected your data for your Blackworm lab at this point and might be wondering how to make a Box-n-Whisker plot with limited sample size. So if you only have 3 sample sizes, you really can't make a Box-n-Whisker plot in the way that we taught you because you can really only graph the median and the max and min. You don't have an interquartile if you only have 3 trials. I also think often mean is a better metric, a better statistic over median. And the reason why in this case it might be better to use mean is if you look at it, this data is different between the different treatments, but the median for all 3 is actually 16. And so instead I'm going to do mean, and I'm going to show you how to calculate that. It's really easy. This version I'm doing right now is in Google Sheets, and there are a lot of things you can do in Google Sheets, but it really is preferable that you use Excel. And if you don't have Excel yet, you need to go to the tech support office and get them to download it. It's free through Kate. And it really is a pretty useful tool. It can be a little clunky and can be a little difficult to learn, but it's something you'll probably be expected to have some practice using when you get to college. So go ahead and get that downloaded. In the meantime, here's how you could do it in Google Sheets. So the way you calculate is you're always going to click on the cell where you want to. Each of these little things is called a cell. You're going to click on that. And this is where I want to calculate the mean of the column of data B. So I'm going to click equals. Now, sometimes it'll autofill equations based on what it thinks you want to do, but in this case it has not. But fortunately, I know a lot of the basic formulas, and the one that you're going to probably use the most is average. I don't know why it's average instead of mean, but that's just what it is. And then it always wants to know what your range of data is, and it wants you to put it in a parentheses. So I'm going to go average parentheses and then highlight those 3. And the B2 colon B4 just means it's taking the average of all the numbers from B2 to B4, so that range. And then I hit enter. You can see it also shows it up in this formula bar. Put enter, and there it goes, 16.333. Now this is the fun part. I don't have to retype that equation every time. I can just click on this one and drag it across. And you might be saying, well, won't it just give the average for column B again and again? And it does not. It's smart enough to understand that it wants it to be C in this column and that you want it to be D in that column. So pretty fun. The other thing I want to calculate really quickly is just standard deviation. So if you remember from the previous video, the central tendency, what's typical, is important when you're presenting your data, but so is the degree of variation within the sample. And this is one of the most important things to remember when you make a graph. So the standard deviation is also really easy to enter. I'm going to put equals st dev, and that is the equation for standard deviation. And then I don't want to include the mean because that's not a data point. So I'm just going to highlight those 3 again. And I'm going to drag this across. And that's pretty easy. The last thing I want to do is I want to do a quick calculation of 2 times the standard deviation. And that is just a convention that if you're plotting too narrow a standard deviation on your graph, you're not being conservative enough and not recognizing the importance of that variation when you're making your comparisons. Most statisticians, most scientists don't actually use the standard deviation. They use something called standard error or confidence intervals, and I'll show you how to do that afterwards. So now I want to make my graph, and the main thing I want to communicate is these 3 values. The mean. So I'm going to insert a quick chart, and I got a lot of choices, right? I could come over here and I could change it to a line graph. It's just 3 points, so it's not going to make a great line graph. I'm going to make it a bar chart, a column chart, mainly because my x variable, my independent variable, is categorical. Orange, blue, and red, which really represents, I think this was a depressant, this was maybe the stimulant, and this might have been I think this was the spring water, and this was the stimulant. I might have those backwards. But it's categorical, so you should always use a bar chart when your independent variable is categorical. Now, that alone doesn't tell me much. It could be a trend that this one was bigger and this one was smaller. But remember, if you don't say what was the variation within the data, you're not really communicating the full story. And so what we want to do is we want to add these error bars. And since it's kind of like the Whisker version of the Box-n-Whisker, it's error bars. Now in Excel, you can add the error bars all at once, but in Google Sheets, you have to do it one at a time. So I'm going to come over and try to expand this so we can see more. No, it's not letting me do that. That's okay. We're going to come over here and we're going to see what happens when I click on this, the blue part of the data, and I'm going to look over to the right and I'm going to actually change it because right off the bat I know that they're mixed up. I'm going to change them to match the actual data. So the orange was plotted in a different color, and so the red is actually that one. There we go. Now it fixes it. So you can see what I just did. Orange, blue, and red were these three, 16.3, 16, and 15.66. So now that's a little bit better, and I'm going to come over here and I'm going to scroll down a little bit under Customize, and I'm going to see something called error bars. Now, right now it's doing the error bar for the red, and because that was the last one I changed. And now I want to represent how variable the data was by putting in a whisker. I don't want it to do 10%. That doesn't really mean anything. I don't want it to do none, but I want to give it a value. In Excel, it would show up as custom error bar, and you would designate the value, and you would usually click on the appropriate value within the data table itself. But in this case, it's going to make us type it in by hand. And if I look over 2 times my standard deviation, that was actually 9.018. Oops, 9.018. And there it's plotted it for me. I'm going to do the same thing with the blue, and I'm going to scroll down here, click error bars, change it to constant, and make it 4, because that was 2 times my standard deviation. Enter. And then finally I'm going to do the last one, which was the orange. I don't love that orange. I want it to, no, that's orange enough. I'm going to scroll down, click error bar, change it to constant, and again, the value is 1.1, can't quite see this, 1.155. Oh, I forgot the decimal, 1.155, enter, and there you have it. And that definitely changes the story. Now I can do all kinds of things, like I can come over here to Chart Editor and I can add titles, I can customize, I can add the title here. Let's see, blackworm, heart rate, blah, blah, blah. I can add a horizontal axis. I can add a legend, right? And I'm not going to worry about that right now, but I just want to show you what this looks like. Now there's a different story going on, right? So even though the orange looked a little higher than the blue, which looked a little higher than the red, our whiskers are clearly visible. There was a large amount of variation within the data for the red and a large amount of variation for the blue, and relatively small degree of variation in our measurements for the orange solution, but you should be able to tell that you cannot statistically conclude that there's a difference between these populations, between these groups. There's just too much variation within the data and too little variation between. Hopefully that makes a little bit of sense. I'm going to do something really quickly, and I want to show you an alternative, and that is the standard error. So statisticians would use inferential statistics instead of descriptive statistics. So mean and standard deviation simply describe the data. The inferential statistics aim to infer to the larger population. So this is where we're trying to make a claim that the things we saw in the data apply to blackworms in these different solutions in general. And so in order to apply that, to infer that to a larger population, we would probably need a really large sample size. And so the standard error is where we own up to our sample size, basically. So the way you calculate it is you would take the standard deviation and divide it by the square root of your sample size. In this case, it's 3. And then we drag that across. And then instead of plotting 2 times the standard deviation, we're going to plot 2 times the standard error. And so that is going to equal 2 times our standard error, and draw that across. And so now we actually see that the error bars for orange would change from 1.1547 to 0.66, and from 4 to 2.3, and from 9 to 5.2. And so I could go back in and I could modify these error bars and go back in and change them. And this one would shrink a little bit, and this one would shrink a little bit. But in the interest of making this a short video, it's already 11 minutes. You guys get the point. It would still be pretty large variation and still a lot of overlap. And typically, you would need to have a larger sample size. A sample size of 3 is never really going to pass muster in published scientific research. The magic standard, according to statistics, is usually around 30, but we don't need to get into that. We obviously had not enough time to do that many samples, but hopefully you learned a lot about how there are a lot of different variables that can influence your data and some of the different ways we can try to minimize that. And hopefully you guys played a little bit with the double blind too, because I am not drawing any conclusions at this point about which of these might be the stimulant and which might be the depressant, because I don't know. And that means that when I look at my data, I'm going to go, oh, yeah, I have no idea which one's which, and so my bias isn't going to make me believe that this is more significant than it actually is. All right, good luck making your graphs. Email me if you have any questions.